Hi, my name is Sun. I am the SARC tutor for Chem 2045. So this is just like a little blurb on things that I have to say. So the review is obviously not a substitute for your textbook or your professor. I kind of put it together mostly using your textbook, so it reflects what Tro thinks will be important, but again, it's not like a catch-all. So one more time, this is the review for Chem 2045. If you're here for another subject, it's fine for you to stay, but I just want you guys to know that the session is going to be live streamed. Yeah, if you feel comfortable, you can stay. If you're in the wrong session, is everyone here for Chem 2045? Yeah, okay, then I don't have to go over that. One last thing, when you guys look around, there are like these papers attached to the table. It's like a survey. If you could, please complete that before you leave and let us know how we're doing. And I don't think there will be any issues with me writing off the page because you can see it, but if I'm doing anything strange, if you can't see, or if I make a mistake, just holler and I will fix it. Do you guys have any questions before we start? Nope? Good? Okay. Okay, cool. So we're just going to start with chapter 1. So I'm going to be switching a lot in between this guy, the periodic table, calculator. Let me know if I'm going too fast. Okay, let's do it. So when you multiply 0.0032 and 23.10, and you multiply them together, how many significant figures will your final answer be? So look here. 23.10. Your answer is going to be something like this. 392. And so the significant figure rules for multiplication state that your final answer should have the amount of significant figures that is like the smallest from the two that you multiply together. So this guy has 2 and this guy has 4. So your answer needs to have 2 sig figs. So you're going to go up to here, and the answer here is going to be D. What's that? Which of the following is a chemical property? So this one is just like a plain memorization one. The difference between chemical and physical is that chemical obviously changes like the way that the atoms interact, whereas physical is just more of almost a reversible change. So the answer for this one is A. I think the only confusing one here would be the smell of paint thinner, but the textbook says that when paint thinner changes odor, it's not actually a chemical change. The atoms themselves aren't interacting differently. Cool. Number 3, a small airplane takes on 245 liters of fuel. If the density of the fuel is 0.821 grams per mil, what mass of fuel has the airplane taken on? So the first thing that you guys should look at here is that the liters and the milliliters are not the same. So that we can't do a lot of math with it yet, we have to make sure that the volume units are similar. So I'm going to do some dimensional analysis and turn this into mils for every 1 liter, or 1,000 mils. So that's going to give you something that looks like this. Right? That's how many milliliters of fuel that you have. And we need to find the mass of this guy. So how do we go from volume to mass? Well, we know that density is equal to mass over volume. And because we're trying to find mass, I'm going to isolate mass, right? Therefore, mass is equal to volume times density. Yes? Oh yeah, I'm sorry. Let's see. Is that better? Kind of. I can. I'm sorry? Zach, can the front lights go off? Well, how about this? Can you guys see this better? Yeah? Okay, then I'm just going to write in pen. Sound good? Yeah. Okay, so volume to mass. How do we get from volume to mass? Density is equal to mass over volume. So I'm going to isolate for mass, multiply by V on both sides. Therefore, mass is equal to volume times density. Good? Right? And we have both of these. We just found our volume up here. So mass is equal to VD, which is equal to 243 times 10 to the third mils, right? And our density was given to us right here. So that's 0.821 grams per mil. Our mils cancel out, and so our M is going to be 201 times 10 to the third, making our answer C. Cool. The first diagram depicts a compound in its liquid state. Which of the other diagrams best depicts the compound after it has evaporated into a gas? So the important thing here is evaporation is a physical, not chemical change, right? So when we see any difference in the way that the atoms are attaching themselves to one another, we know that that's a chemical change, and that can't be the answer. So we have a gray, a white, and a gray all together as one unit. And the only one that matches that is A here, right? Everything else, B, C, D, all of the atoms seem to connect in a different way, which shows that a chemical change has taken place. So the answer here has to be A. What is a pure substance? This one's also just like a memorization question. There's always like 1 or 2 questions on the final about something like this, so while it's kind of annoying to memorize, I would just learn it for the sake of learning it here. Pure substance is basically just anything that can't be separated into a simpler compound, right? So lemonade, salt water, paper, these can all be separated into similar compounds, but copper is a pure element, so that has to be our answer here. Is the speed I'm going at okay? Mm-hmm. Yeah? Okay, yes. Could you speak up a little bit? I'm sorry.
Is the packet, like, can I find the packet online?
Yes, okay, yes. It is going to be UCF Study Union.wordpress.com. It's going to be under Chem. My name is Sunmi. Jin. You guys can just call me Sun. And you're going to see links to PDFs when you find my name. The page is pretty long, so yes. And just another thing, if you guys are like concerned about getting like everything down, I am being live streamed, and I think it's going to be up later. So don't feel worried. You're going to have access to the video later. Good. Okay. Chapter 2. A naturally occurring sample of an element contains only 2 isotopes. The first isotope has a mass of this guy and a natural abundance of this guy. The second isotope has a mass of 70.92, and they want you to find the atomic mass of the element. So make sure you're aware of what they're asking you. They're not trying to ask you to find the natural abundance of the second isotope. They want you to find the atomic mass that you would find like on a periodic table, right? So how do we do that? Well, the way that we find atomic mass is that we have 2 different isotopes here. If you have 3 or 4, then you would have 3 or 4 different isotopes written down. But you would take their mass, right? You would take their mass and you would multiply it by the decimal of their natural abundance. Right? And so your mass here is 68.9255. And the mass of your second one is 70.9247. And the natural abundance here, they give you 60.11%, so I'm going to put this as my natural abundance. And I don't have something here, so that's unknown. But when I add these up, I should be getting my atomic mass, right? So it looks like at first sight we have 2 unknowns, but that's actually not the case because we only have 2 isotopes. This one has to be 1 minus 0.6011, right? Because you can't have more than 100%. What this is really saying is that of the 100% of isotopes in the universe, and there are only 2 isotopes in existence, this makes up, the first one makes up 60%, so the other one has to make up 100 minus 60%. Good? So what we're going to do is 68.9255 times 0.6011 plus, and I'm going to make this a bracket, 70.9247 times 1 minus 0.6011. When you do the math out, you should be getting an answer like this. And the answer to that would be B. Everyone understand how I use the percentages and decimals to get to there? Good, good. Number 7, which pair of elements do you expect to be most similar? So this is like a periodicity or a trend kind of question. Essentially, there are 2 different types of groupings in the periodic table. There are periods, which go across like this, and there are groups like this. What's really interesting about the periodic table is anything in the same column tends to display similar physical and chemical properties. So when you look at this guy, 7, nitrogen and nickel are not even in the same area, right? This is a gas, this was a metal, so it can't be A. Molybdenum, MO, and tin here are in the same period, but they're not in the same row. In the same period, but not in the same column. So I would keep that on the back burner. Sodium and magnesium, these are also pretty similar, right? They're both metals, but they're not in the same column. Finally, these are my halogens, chlorine and fluorine. These behave very similarly. Anything in the same column is going to have very similar attributes. So the answer here is going to be D. How many silver atoms are there in 3.78 grams of silver? So they give you a mass and they want you to tell them physically how many actual atoms do you have here. And as you can see, I've given you the molar mass I want you to use. So in 3.78 grams, right, the first thing I ever want to do in any stoichiometry problem is convert to moles, right? And so I have my grams here canceled out, and so I'm stuck with moles. Once I do this out, I'm going to get moles. But they're not asking for moles, they're asking for how many atoms there are, right? So we all know that in 1 mole, it's going to be 6.02 times 10 to the 23 atoms. And now I can cancel this out. Multiplying across and dividing by that, I'm going to get 3.78 times 6.02, 10 to the 23. I'm going to divide that by, and the answer for 8 should be C, which is 10 to the 22. Okay. This is also just another conceptual question. So they're asking you to tell them what you think that ionic bonds can do. So ionic bonds tend to form between a metal and a nonmetal, or ionic bonds tend to form molecular compounds. Ionic bonds involve a sharing of electrons, or ionic bonds form bonds between a cation and a zwitter ion. So the only one that seems to make any sense here is A, right? If ionic bonds were to form bonds, they would be between a cation and an anion. Ionic bonds don't involve the sharing of electrons. This is a very unequal kind of relationship in which one atom gets all of it and the other one gets none of it, right? So this is not sharing, this is transfer. They don't form molecular compounds, they form ionic compounds, right? So here has to be A. On the other hand, this is just a side note, the thing that forms between 2 nonmetals is covalent bonding. Cool. On to nomenclature questions. The name of this compound is, and they want you to tell them what the answer is. So we know that Pb is lead, right? So Pb here is lead. They could trick you with different things that look like it could be the answer, like polonium and palladium. Polonium is Po and palladium is Pd, but Pb is lead. Okay, so B and D are out of the question. And now they want you to tell them what this is right here. So we should know that this is the acetate ion, right? And, well, actually, I read that as lead. It can't be tin either. Tin is Sn, sorry. So this is the only one that makes sense, right? Good. Another quick note, this number here is not the number that would go there, right? This is actually the charge of the lead ion. So this is not Pb2C2H3O2. It's not what that is. It's the actual charge. Good. the coefficients for the balanced equations are, and so I know this is kind of confusing, but essentially like where each number goes, here, here, and here. Okay, so there are a lot of different ways to balance equations, but the one that I found tends to work best is writing out which ions you have in like a column format to make it easier on the eyes. So here I have 4 hydrogens, right? Well, no, I don't. I have 2. And I have, oh, sorry, I made a mistake. That's why I was like, wait. I do have 4 hydrogens. And I have 2 nitrogens. And here I have 3 hydrogens and 3 nitrogens, right? So where do I start from here? So pro tip for balancing equations, start with everything except C, H, and O, because these are really hard to balance. You want to balance everything except for these guys first. And then once you've balanced all of your other atoms like nitrogen or chlorine or fluorine, then you're supposed to go in this order. Balance carbon, hydrogen, and then oxygen. So as we can see here, the first thing we're going to want to balance is nitrogen, right? So we have 2 on this side and 3 on this side. That's not like a nice even distribution. And the only way to get them to be the same is to multiply them by each other, right? Finding the least common multiple. And so what I'm going to do is I'm going to multiply this left side by 3. No, I'm not. I'm going to make the nitrogens on this side 6 and the nitrogens on this side 6. Right? So in order to do that, I'm going to have to give this guy a 3, right? In order to make this nitrogen a 6. And in order to make this nitrogen a 6, I'm going to have to give him a 4. That way I have 4 nitrogens plus 2 nitrogens will give me 6. Right, so we've balanced these guys. Let's see where our hydrogens lead us. So now we have 4 times 3, which will give us 12. And then we have 3 times 4, which will give us 12. So coincidentally, in this problem right here, by balancing our nitrogens, our hydrogens also balanced out, right? And so our coefficients are 3, 4, and 1, which is A. I never highlighted this, sorry. A chemist decomposes samples of an unknown compound. The mass of its constituent elements are listed. Calculate the empirical formula, and they tell you that the molecular weight of silver is 107.87 grams, and then they give you the molecular weight of oxygen as well. What did I just do? Okay. First thing we want to do is get, this is what they give us, right? We want to get these guys into moles. And the purpose of the empirical formula is, okay, we have our chemical formulas for something like glucose, which is like my go-to, right? But the empirical formula for that is actually this. So it's basically like the least common denominator for all of these. It's been divided by that. And it gives us like the ratio instead of the actual chemical formula. So we're trying to find the empirical formula. In order to do that, we have to get everything in moles because everything in chemistry is centered around that concept. So with 1,651 grams of silver, for every 1 mole, that's how many grams you have, right? Grams, Ag have been canceled out. That'll give us this many moles, 0.1530 moles. Good. And then we're going to do the same with oxygen. If we have 0.1224 grams oxygen for every 1 mole, you have 16 grams, right? So our grams cancel out. And that should give us, if we do our math correctly, this many moles of Ag and oxygen, right? So what does this look like right now? Right now we have Ag 0.01530, oxygen 0.00765, right? This isn't like a super pretty looking empirical formula, so we're going to divide by our smallest number, which this one is smaller than that one, right? So we're going to divide by this one. And when we divide 0.00765 0.01530 divided by this guy, we get 2 exactly. So we're going to get Ag2O, which is B. So with empirical formulas, just get to the moles and then find their ratios. The names of these compounds are, so they give you HI and HClO2. So HI is a binary acid, and then HClO2, is an oxy acid. So the thing about binary acids is that they're very easy to name. You're just going to write hydro, whatever its name is here, I'm going to put acid. Right. So here this would be hydroiodic acid. If you had something like HCl, it would be hydrochloric acid. And if you had Br, it would be hydrobromic acid, right? So it has to be hydroiodic. Is that right? Yeah, okay. So we can get rid of A because this is hydrogen iodide. We can get rid of C because this is hydrogen iodide. These two are correct, B and D for hydroiodic acid, right? So let's turn our attention to these guys. What's the answer for 13? Okay. These guys are a little bit harder to name. Oxyacids have a more convoluted nomenclature system, and it all depends on the number of O's that you have, right? And so this is just a memorization thing. If you have, these are the common possibilities, right? So this is going to be perchloric acid. This is going to be chloric, chloris, and what is this? Hypochlorous, thank you, yes. It's going to be hypo, this is going to be per, right? This is going to be chloric and chloris. So because we have 2, it's going to be chloris. Chloric acid would be HClO3. So this guy is D. Good. So 14, copper 2 fluoride contains this much fluorine by mass. Calculate the mass of fluorine in grams in this many grams of copper 2 fluoride. So when they give us this information, we can take advantage of it by pretending like for every 100 grams of copper 2 fluoride, 37.42 grams of it is going to be fluorine, right? So we take advantage of that by writing this kind of proportion out. Well, we don't have 100 grams of copper 2 fluoride. We have 55.5. So they're asking us to find how many grams of fluorine would be in this amount. Well, what we've just done is set up a proportion, right? So if for every 100 grams we have 37.42, then how many do we have in 55? So I'm just going to cross multiply and get my answer. So 37.42 times 55.5, and I'm going to divide that by 100. I should get 20.76 grams, which is right here. Good. Chapter 3. Chapter 4, for the of the, what? I'm sorry. So for the following acid-base reactions, calculate the mass in grams of the acid necessary to completely react with and neutralize this many grams of the base, right? And so what this problem depends on is you being able to differentiate between your acids and your bases, right? This should be pretty easy because you're required to know what your strong acids are. This is a strong acid, it's nitric. And you're required to know what your strong bases are, and this is a strong base, it's calcium hydroxide, right? So we know that our base here is calcium hydroxide, and our acid here is H and O3. First thing we're going to do is figure out how many moles of our base we have to work with. So if we have 4.85 grams of CaOH2, they tell us that for every 1 mole weighs 74.09 grams, right? So we can cancel this out. And we know that given this equation, right, we know that for every 2 moles of acid, it only reacts with 1 mole of base. So I should have actually written CaOH2 down here. For every, what did I do? For every 1 mole of CaOH2, we have 2 moles of HNO3. And then we're going to, once we've canceled this out, we're going to come back to see how many grams, calculate the mass in grams of the acid, right? So now that we have the number of moles of acid, we're going to say for every 1 mole of acid, we have 63.02 grams, which we can cancel out here. So now once we do our math, we should get 8.25 grams HNO3, which is right here. Good. 16. Zinc sulfide, which is this guy, reacts with oxygen according to the reaction. A reaction mixture initially contains 4.2 moles of zinc sulfide, 6.8 moles of oxygen. Once the reaction has occurred as completely as possible, what amount in moles of the excess reactant remains? This is kind of like a 2-part problem. First, in order to find our excess reagent, we basically have to find our limiting reagent, right? And then once we found that, we have to figure out, okay, how much doesn't actually react? Because that's what our answer choices are reflecting. So first things first, let's find our limiting reagent. So there are 2 situations that could occur here, right? So they give us 4.2 moles zinc sulfide, 6.8 moles oxygen. This is all we have to work with, right? In the real world, this is all we have to work with right now. So let's say situation 1, I use all of my zinc sulfide. So all 4.2 moles of zinc sulfide are going to be used. Then how much oxygen would I need to satisfy that criteria? Let's find out. So for every 3 moles of oxygen, right, I use 2 moles of zinc sulfide. So where would that leave me? 6.3 moles of oxygen. Okay, so this is possible, right? Because if I use all of this, I still have some left over here. So in situation 2, if I were to use all of my oxygen, then how much zinc sulfide would this demand? 6.8 moles of oxygen. We use 3 moles of oxygen for every 2 moles of zinc sulfide. Once we do the math out here, we would need 4.53 moles zinc sulfide. This is impossible to follow through on because we don't have that much zinc sulfide. We only have 4.2, so this is not viable. And this is what we have to use, right? So we found out that zinc sulfide here is our limiting reagent, and oxygen here is our excess, right? They want us to tell them what amount in moles of the excess remains. So we used all of this. This is gone. But of the 6.8 that we have, we only use 6.3. So how much remains? 0.5, which happens to be B. All right, lead ions can be precipitated from solution with KCl according to the reaction. I'm going to highlight this because this is pretty text heavy. When 28.5 grams of KCl is added to a solution containing 25.7 grams of Pb2+, a PbCl2 precipitate forms. This precipitate is then filtered, dried, and found to have a mass of 29.4 grams. Determining the limiting reagent, the theoretical yield in grams, and the percent yield. So this is a 3-part problem. And as you can see, these are all divided into 3 parts like this. Right, so this is our limiting reagent, our theoretical yield, and then our percent yield. So first thing we're going to want to do is do the same thing that we did back here, except that these were given to us in moles. This time they're given to us in grams. So we have just one extra step. We have to find our limiting reagent first, theoretical, and then percent yield. Okay? So let's figure out how much we have to work with. I'm going to, actually, I don't think I'll have enough room, so I'm going to do the conversion up here, and then I'm going to jump down here, okay? So with 17, they say that you have 28.5 grams KCl, right? And, yeah, let's do that one first. So you see down here that they give you the molecular weight for that. So for every 1 mole KCl, you have 74.45 grams KCl, right? And then you can cancel this out. How many moles do we have? We have 0.382 moles of KCl. And then next, because we just did this guy, we're going to need to figure out how many moles of Pb2 there are. So they give us 25.7 grams of Pb2 plus. For every 1 mole of Pb2 plus, they tell us it weighs 207.2 grams. I'm going to cancel that out. Should get a number like this. Right, so now I'm back at the place where I was in the last problem. This is how many moles I have to work with. So in situation 1, let's say I use all of my KCl, 0.382 moles of KCl. According to my problem here, for every 2 moles of KCl that I use, I need 1 mole of Pb2 plus, which will demand 0.191 moles of Pb2 plus. This looks impossible right now, right? Because I don't have that many moles of Pb2 plus. I only have this much, so this looks impossible. Let's look at the second one. If I use all of my Pb2 plus, right, I use all 0.124 moles of this guy. For every 1 mole of Pb2 plus, I need to use 2 moles of KCl. If I do that properly, I should get a number like this. 248, sorry guys, 248 moles KCl. This is possible, right? I have much more than that at my disposal. So it looks like Pb2 plus is going to be my limiting reagent, right? The limiting reagent is Pb2 plus. Looking at my answers, it can't be A because that says potassium. That doesn't even work, right? Because potassium isn't actually one of my reagents. And it can't be U either. So it has to be B or D. I've already eliminated my answer choices by half, right? Next, I'm going to find the theoretical yield of PbCl2 in grams. So when I, where am I? Right, how many moles of Pb2 do I have? Here, sorry, okay. My limiting reagent is Pb2 plus, right? And so that's the thing that I have to start with. That's what's going to determine what direction my reaction goes in. So I start with U, and I think, how many moles of PbCl2 can I make given the limited amount of Pb2 plus that I have? These guys are in a 1-to-1 ratio, if you guys see that. So that's going to be the number of moles of PbCl2 I can make, right? And then they give me the molar mass here. So for every 1 mole of PbCl2, it weighs 278.11 grams. Canceling this out, I should get 34.485 grams, right? Which is this guy. What I've done here is, in a perfect world in which all of my limiting reagent is converted into a product, this is how much I should be getting. However, they tell us that they did the experiment themselves, and experimentally, this is what they got. So they didn't get 100% efficiency. They want us to find how effective was it, in which case, I'm going to write up here because I'm actually out of room, sorry. knowing that I was supposed to make 34.5, but I only made 29.4, and multiplying that by 100 to get a percentage. I had an 85% efficiency. That has to be B. I know that's a long-winded problem. Cool. 18. What is the net ionic equation for the reaction that occurs when aqueous solutions of potassium, what is that, bicarbonate, and HBr, hydrobromic acid, are mixed? So this requires you to know your solubility rules, right? What is soluble and what is not, or what likes to ionize and what doesn't like to ionize. And it also requires you to know something called your gas evolving reactions. So when you see anything like this, or anything like this, you should know that eventually they're probably going to make carbonic acid or sulfuric acid, which like to dissociate into gas and water, right? And so when we mix these guys up, what's going to happen? When we mix these guys up, let's say I just add them together like this, they're going to make KBr, and they're going to make H2CO3, right? This guy is aqueous, and both of these are aqueous, by the way. This guy is aqueous, but this guy is going to dissociate further, specifically, into water and carbon dioxide, right? So although it's not a precipitate, it doesn't have the ability to be canceled out in a net ionic equation like I would with potassium and bromine because of the fact that it's going to break down further. And water is a liquid and CO2 is a gas. These guys cannot be canceled out either. They're not aqueous. And so what I wind up with is, What I wind up with is the two reagents that wind up making H2CO3, which is this and this right there. So that's my proton, that's HCO3 minus, and it's going to make my gas and my water. So it's got to be C. No, sorry, B. Right? Yeah. How many moles of KCl are contained in this solution? And they just give you a situation. So you have 556 mils, and then you have in here a 2.3 mil KCl solution. Well, first thing I would do is turn this into liters because we're working with a unit that is moles per liter, right? So 556 mils. For every 1 liter, there are 1,000 milliliters. So this is how many liters I would have. And then, given my molarity, 2.3 moles per 1 liter, knowing that I have 0.556 of a liter, how many moles do I have? Doing a proportion, 2.3 times 0.556 divided by 1, I should get 1.28, which is my answer. Identify the oxidation numbers for PB and state whether it is oxidized, reduced, or neither. Hold on. All right, so this one requires you to assign oxidation numbers for everything. Quick oxidation rules. Oxygen is always going to be -2, except in H2O2, in which oxygen is going to be -1. But for the most part, in any other situation, you're going to find it. It's going to be a -2. Fluorine, always -1. The more, this is electronegative atom, gets priority. So you're going to assign its oxidation number before you assign anything else's. And just a tip, be careful of subscripts. So when we look at this guy, oxygen here is going to have a -2. Actually, this is really cramped. I'm just going to show you guys my notes here. So if you look at number 20, oxygen is going to have an oxidation number of -2, right? But you have 3 oxygens, and then you have to multiply that by 2, right? You see how you actually have 6 looking at the subscripts here? So 2 times 6 is -12. So what I'm writing down here is the actual oxidation number for everything. What I'm writing up here is a check in order to make sure that all of my oxidation numbers add up to the overall charge. So because PbNO3 doesn't have a charge up here, all of these need to add up to be 0. That's how I am going to assign my oxidation state to my other atoms, right? So oxygen gets assigned at -2. Nitrogen could either be assigned a -3 or a +5, depending on where it is in the periodic table, right? Because it's 1, 2, 3 from the right, or it's 1, 2, 3, 4, 5 from the left. So it can be either a -3 or a +5. But in order to make this, like this is a huge negative number, right? In order to get that back up to 0, I'm probably going to have to assign it a large positive number because I only have 2 nitrogens. So when I give it a +5 and I multiply that by 2, I'm going to get a +10, which perfectly represents Pb's usual charge or oxidation state of +2, right? So that's how I did that. Over here, oxygen, like I said, always gets what it wants, so it has a -2. But you have 4 oxygens, so 2 times 4 is going to give you -8. Sulfur, as you can see, can be a -2, but it can also be a +1, 2, 3, 4, 5, 6, which is why I have assigned it an oxidation state of 6 here. And Na is going to have, what is this? This is a +1, right? Because Na is over here. It's a +1. In order to get that to cancel out and become a 0 here. And then same thing here, oxygen has a -2. You have 4 of them, so 2 times 4 is -8. Sulfur does the same old here. And then Pb is going to keep its +2 here in order to keep, when you add all these up, it should equal 0. And -2 times 3 is -6. Nitrogen likes to have a +5, and sodium likes to have a +1, which also balances out to have a 0 charge, right? So what was the original question here? Identify the oxidation numbers for Pb and state whether it is oxidized, reduced, or neither. So when I look at my numbers for Pb, right, they haven't changed. This guy hasn't changed at all. So it has been neither oxidized nor reduced in this situation, right? And this is the only answer that fits that here. I know you guys have probably heard of this mnemonic, but oil rig is something that is really helpful. So oxidation is a loss of electrons, and reduction is a gain of electrons. So actually, even though it's called reduction, your number is going to get more negative. Because when you're reducing, what we're talking about is the oxidation number itself is getting reduced as it becomes more negative. But you're gaining electrons, which themselves have a negative charge. So you gain something that has a more negative charge, and thus you become more negative. It's a crash course on oil rig. Okay, on to thermochem. We're doing on time. Good. A system releases 622 kilojoules of heat and does 105 kilojoules of work on the surroundings. What is the change in internal energy? So the equation for this guy is just delta E is equal to Q plus W, and the signs of Q and W depend based on whether you're doing work, getting work done on you, releasing heat, or taking in heat. So here, you're releasing heat. That shows you have a negative sign here because the heat is leaving. And then you're doing 105 kilojoules of work. So that's also negative. You're expending energy. So both of these are negative. Negative 662 plus negative 105, which is going to give you negative 767. And 67, what?
I think it's negative 622, 662.
It is 622, you're right. 622, right? Plus negative 105, negative 727, right? And that is going to give you this guy. Because, so these look different, but they're actually the same answer. Because if you put a point sign here, or decimal here, and you moved it over twice, you would get the same answer that you started with, right? Okay. (22) Nitromethane, which is this guy, burns in the air to produce lots of heat. This is your equation right there. How much heat is produced by the complete reaction of 5.56 kilograms of nitromethane? First thing you want to get that to is moles, right? So if I have 5.56 kilograms of nitromethane, in every 1 kilogram, there are 1,000 grams. And I gave you the molar mass of nitromethane here. So for every 1 mole, I'm going to have 61.04 grams. Right? So my kilograms cancel out, my grams cancel out. That should give me, for number 22, I should get 91.1 moles of nitromethane. So what this equation is actually telling us is that for every 2 moles of nitromethane that are burned, this much heat is released, right? Because this is our enthalpy. This is our, you can't really see that, can you? It's negative 1418 kilojoules. And so they want us to tell them, okay, knowing that this much heat is released for 2 moles, how much heat is released by 5.56 kilograms, which happens to be that many moles, right? So this is just actually a simple proportion. Knowing that for every 91.1 moles, that's what we start with, we know that for every 2 moles, that much is burned. What does that look like to us? 91.1 times 14, or negative 1418, divided by 2. It's going to give us negative 64589.9. And when we round, that's going to be negative 6466600. And then we're going to go 1, 2, 3, 4. So it's actually going to be negative 6.46 times 10 to the 4th, which is right here. When 0.514 grams of biphenyl, this guy, undergoes combustion in a bomb calorimeter, the temperature rises from 25.8 to 29.4. Find the delta E of reaction for the combustion of biphenyl in kilojoules per mole. The heat capacity of the bomb calorimeter determined in a separate experiment is this guy. So bomb calorimetry is a little bit different from like coffee cup calorimetry in that the equation that you use is just Q equals cat. There's no mass needed when you're doing calorimetry in a bomb calorimeter, right? So Q equals cat, and they give us our C because it was determined in a separate experiment, right? So Q is going to be equal to 5.86 kilojoules per Celsius, and our change in temperature is going to be final minus initial, right? So what is that? It's 29.4 minus 25.8, which gives us 3.6 degrees Celsius. So our Q here is actually going to be 21.096. The Q that we just found is actually a Qcal. Qcal, right? It's the heat of the calorimeter. We're not interested in the heat of the calorimeter. We're interested in the heat of the reaction. Incidentally, the heat of the reaction is equal to the negative Qcal. So this, what we're interested in is actually negative 21.096 kilojoules, right? Again, however, they ask us to find delta E of reaction, which is not what our Q reaction is. Delta E of reaction is our Q reaction divided by the number of moles we have. This is a standardized unit, so it's going to be Q reaction divided by number of moles, right? That's where this grams comes in. So a lot of people get confused when they see the grams and a bomb calorimeter together in the same question because they think, oh, well, I don't have a place to put that mass. It's because we need to find the number of moles from this in order to find our delta E of reaction, right? So knowing this, we have to find our number of moles. So 0.514 grams of biphenyl. I gave you the molar mass here. So for every 1 mole, we have 154.2 grams, right? So how many moles do we have? 154.2 times 0.514. That should, is that our number of moles? No, that's not it. What did I do? Oh, I needed to divide. 4.2. So that should give you 0.0033 moles. We're going to divide our Q reaction by our number of moles, as stated here. So negative 21.096 divided by that. It's going to give us something like negative 6392, which we round to here because it's negative 63. It should actually be 4, but yeah, times 10 to the third. So our answer here has to be B. 24, calculate the delta H of reaction for the reaction, right? So this is our goal here. What is this? This looks like Hess's law, right? So, I'm coming off the page, sorry. Look at this guy. If this is our goal reaction and this is what we have to work with, the best way to try to approach Hess's law most of the time is to go reactant by product, right? So looking at 5 carbon, we know that we have to get 5 carbons on the left side using these guys. The only thing that we can really see here is to multiply equation number 2 by 5, right? And by doing so, we get 5 carbons on the left. We don't have any isolated carbons anywhere else in this. So we're going to multiply this guy by 5, right? So we've got that down. And then let's look at our H's. Where are our isolated H's? They are down here, right? So if you look through, we also don't have any other isolated H2s. The only ones that I can find are right here. So we're going to multiply this by 3. Finally, our cyclopentanes are over on the right in our goal equation. But here, the only cyclopentane that we have is on the left. So in order to reverse an equation like this, you can just multiply by -1, which will flip your equation, right? So having done this, I'm going to write out what I would get if I were to do all this. So equation 1 would turn into 5 carbon dioxide plus 6 waters is going to give me C5H12 plus 8 O2, right? Equation 2, I would multiply everything by 5. In equation 3, I would multiply everything by 3. Right? And so everything winds up canceling out in a way that we are able to get our goal equation. This is on the left side of the arrow, this is on the right side of the arrow. We have 3 plus 5 is 8 on the left side and 8 on the right side, so these all cancel out. So we're left with cyclopentane on the right and these guys on the left, right? So we know that the math that we've done here is correct. Knowing that, multiplying this by 1, we're going to get 32,448, which is positive. Multiplying this by 5, we're going to get negative 393.5 times 5, negative 1967.5, and multiplying 483.5 times 3 is going to give us negative 1450.5. When we add all of this together, should get negative 173.2, which is D. 25. A 31.1 gram wafer of pure gold, initially at 69.3 degrees Celsius, is submerged into 64.2 grams of water at this temperature in an insulated container. Find the final temperature of both substances in thermal equilibrium. So this is a really math-heavy problem. What we're going to do is, this is not a bomb calorimeter problem, but it's still a thermochem problem. So we're going to use Q equals MCAT here. Right? There are two things to look at here. We have water and we have gold, right? Because here is our tub of water and we're going to put gold in here. So however you choose to look at it, whether this is the system and this is the surroundings or vice versa, the Q of the gold is going to be equal to the negative Q of the water. And this makes sense, right? Because all of the heat lost by the gold or all of the heat gained by the gold is also in turn lost or gained by the water because they're in contact with one another. So this is what we're going to be using. We're going to say MCAT of the gold is equal to negative MCAT of the water, right? So now I'm just going to start plugging. The mass of the gold is 31.1 grams. The specific heat of gold is given, and it's 0.128 joules per gram Celsius. And our change in temperature is kind of funky. We don't have our final temperature for either of these, right? We have where the gold started, and we have where the water started, but we don't have the final temperature. So what I'm going to write here is T final minus T initial of the gold, right? Same thing over on this side. It's going to be negative, however. Don't forget that negative sign. The mass of the water is given, 64.2 grams, and the specific heat is given, joules, grams Celsius. This is going to be T final minus, see if I can squeeze this in here, 27.8 degrees Celsius, right? So now what we've got to find is our TF, and we've got to isolate that. So instead of writing this out, I'm going to show you guys the work that I've done. Here, this is 25, right? So you can see I've already plugged everything in here. When I multiply 31.1 times the specific heat, so the mass times the specific heat, I'm going to get 3.98 joules, right? And I keep everything else here the same. And when I multiply the mass times the specific heat here, I get negative 2.68, well, actually 268 joules per Celsius. And then I bring this down. What I'm now doing is I'm isolating the TF term on this side. I divide by 3.98 on both sides, as you can see. When I divide 268 by 3.98, I get this answer. I bring this down and I bring this down. Now I am expanding in order to get my TF term to this side. You see what I'm doing? So I multiply 1 TF times negative 67.3, which is going to be like this. And when I multiply this by this, I get this answer. And in order to add my TFs together, I bring this over to the side, which is going to go from 67.3 to 68.3. And then I divide by 68.3 on both sides to get my final TF like this. So I know that's actually like a lot of actual algebra and like rearranging, but that's how you're supposed to find your temperature final when you have two different, a system and a surrounding like that, if that makes sense. Did we get all of that? I know that's kind of tough. Yes? Why did I make this negative right here? Yeah. Okay, so this little diagram that I drew, right? We have our water bath and we have gold that we're putting in, right? So in my head, how I like to think of it is that our gold is our system and our water is our surroundings, right? And so any heat that is lost by the gold has to be taken up by the water. And any heat that's lost or taken up has to be lost, right? So they're in like an interconnected relationship where if this guy loses heat, it gains, right? So the signs for the heat is switched for gold and water. Does that make sense? Right, so it doesn't actually matter if you put the negative sign on this side or on that side. The math is going to work out to be the same. So I just did it because I like putting the negative sign second. I'm not sure why. But if you guys were to do it so that you put the negative sign here, your math would still work out to be the same. Good? Okay. Any other questions? Good, okay. 26. Oh, I didn't give you the answer for that, did I? It's 28.41 which will give you C. Yeah. On to Chapter 7. A heat lamp produces 32.8 watts of power at this wavelength. How many photons are emitted per second? And they tell you that 1 watt is equal to 1 joule per second. The speed of light is 3.0 times 10 to the 8th meters per second, and Planck's constant is this guy. So I've given you like your typical constants like C and H. First thing that we need to know is that the energy of a single photon is equal to Planck's constant times the speed of light over a wavelength. That's an H. Plugging that in, I'm going to do Planck's constant times the speed of light. What is it? 3.0 times 10 to the 8th. And then I'm going to divide it by the wavelengths that they've given me. But wait, I forgot to 6.5 micrometers. For every 1 meter, you have 10 to the, no. For every 1 micrometer, you have 10 to the negative 6th meter, right? So that's something that a lot of kids get tripped up on. Remember that, like think about it logically. You're not going to have a million meters in a micrometer, right? So just take a step back and look at what you're writing, and if it doesn't make any sense, just flip it. And so I actually wrote this incorrectly. I should have actually put this on top and this on bottom, but we know that 6.5 micrometers is going to be 6.5 times 10 to the negative 6th meters. Does that make sense? This equation, because the speed of light is written in meters per second, you cannot use micrometers as your wavelength. You have to put meters here, which is another reason why I know that a lot of the work can get like long and drawn out, but writing units is super important because it's like a fail-safe, making sure you're writing the correct numbers into your equation. So I multiplied the speed of light times Planck's constant, and I'm going to divide by this number now. So the energy of a single photon is going to be 3.06 times 10 to the negative 20th joules, right? But they don't actually ask for the energy of a single photon. They ask us how many photons are emitted per second, right? And so knowing that this is actually 32.8 joules per second, right? That's how much energy is produced by this heat lamp. We're going to divide this by this to figure out how many photons are emitted. Because this is the total energy divided by the energy of 1 photon. When we divide those, we should get the number of the amount of photons that we're getting.
Did you say that one more time?
Yes. So this guy, right, like we have like this little lamp here. And it's emitting this much light, right? And this is the total amount of energy that the sum of all of our photons are emitting. However, what we have, or what we just calculated, is the energy of 1 single photon, right? And so when we divide energy total by the energy of 1 photon, we should get the number of photons. Does that make sense? Yeah? Okay. So we're going to do 32.8 divided by our energy of photon, right? So 32.8 divided by, this is the energy of my photon. 32.8 divided by 3.06 times 10 to the negative 20th. It's going to give me 1.07 times 10 to the 21st. And 26 is A. Good. Cool. So this one's about quantum numbers. This is also just like memorization. So N, L, ML, and I think it's MS, which is not specified here. These guys basically tell you everything you need to know about an electron. So N tells you what shell the electron can be in, right? So N is actually corresponding to the rows on the periodic table. This is N equals 1, N equals 2, N equals 3. So all of these are valid, right? Because we have up to 4 rows on our periodic table. However, L is what tells us how many, or what kind of subshell it's in, right? And so when we have n equals 1, or n equals 2, or n equals 3, L can be anything up to n minus 1. That's the max that it can go. Does that make sense? And it corresponds to S, P, D, and F, right? So S has a 1, P, or I think S is 0, P is 1, D is 2, F is 3. And so when we look at, I don't know, for example, row 3, it can only have up to 2. It can only have up to a D subshell, right? Row 3 does not have an F subshell, which is why that having an L that is equal to an N doesn't make any sense. So that obviously, like as soon as we look at it, we should be like, oh, that looks weird, because N here can go up to L equals 1, L here can go up to 2 and 3, so these all make sense, but this one doesn't, because 3 cannot have an F subshell, so it has to be C. Does that make sense? And then just as a side note, ML can be anything from negative L to L. So if we have, for example, let's say that our L number was 1, meaning that our electron was in a p shell. We only have 3 total different kinds of p shells, right? We have one that goes up and down, left and right, and in and out of the paper, right? So that is 1, 2, 3. And so we can have a -1, 0, and a +1. So for D, we can have like a -2, a -1, a 0, a 1, and a 2, and that's because we have 5 different D subshells, and that's the way that our quantum numbers work. That was just a little side note. Obviously, C has to be the answer because L can't be equal to N ever. 28, calculate the wavelength of light emitted when an electron in a hydrogen atom makes the transition from 2 to 1, right? So what it's doing is it's jumping down and thus emitting light. So the equation for this is -2.18 times 10 to the -18th times 1 over n final squared, 1 over n initial squared, right? And so what is this going to give us? Our n final was 1, and our n initial was 4, right? So if just looking at this, 1 over 1 squared minus 1 over 2 squared is going to give me 1 minus 1/4, right? So this term right here is actually 0.75, or 3/4. So I'm going to do -2.18 times 10 to the -18th times 0.75. It's going to give me -1.635 times 10 to the -18th. And this is our energy emitted, right? But we don't want to know the energy emitted. We want to calculate the wavelength of the light emitted when an electron in a hydrogen atom makes a transition, right? But we needed to have this because our wavelength equation comes from something that looks like this, right? And when we isolate for wavelength, it looks like this. And we can't get our wavelength without first calculating our energy. So we're going to use Planck's constant, 6.626 times 10 to the -34th. Multiply it by the speed of light. And divide it by the energy that we just got. -1.63 times 10 to the was it -18th, right? And our wavelength is going to be -1.21 times 10 to the -7th, which happens to be this one, actually. I don't know why I wrote it like that for the answer. I should have written it like this. But, I mean, that's fair game as well, because we should be able to look and see, okay, if we move this 1, 2 to the right, we also have to move this to -9th, which has to be the answer. Good.
What happened? 0.75?
Here, yes, 0.75. because it's 1 over 1 squared minus 1 over 2 squared, which is 1 over 1/4, which is 3/4,
Yeah.
which is 0.75. Yeah, okay. 29. According to Coulomb's law, which pair of charged particles has the lowest potential energy? So this requires you to know what Coulomb's law is. Coulomb's law says that the potential energy is equal to the charge of the first times the charge of the second over the radius, right? I'm going to show you what I did here. Do we see that? Good, okay. So you have A, B, and C with different things, and D claims that they all have the same potential energy. So what I did was, in choice A, you have a -1 charge and a +2 charge divided by your radius, right? Charge, radius. So -1 times +2 divided by 150, and I did that for choice A, B, and C, right? And when I calculate this out, don't be tricked by the negative sign. You want the smallest number to give you the lowest possible potential energy, right? So this looks larger because it's 0.030 as opposed to 0.006, but it's more negative, so you'd want to pick this one. So the answer for 29 is going to be C. Consider the set of ionization energies. So when we look at this guy, ionization energy is the amount of energy needed to rip an electron off of an atom. The jump here happens between 3 and 4, right? That's an enormous jump. Like these are definitely like, this is like 1,000, this is another 1,000, this is like 9,000, right? So it happens between the third and the fourth. Which third period element do these ionization values belong to, right? Third period is over here. And keep in mind, your ionization energy is going to jump when you rip an electron off of a noble gas. Because once noble gases have reached their perfect octet and they have 8 electrons around them, they're very stable and non-reactive, and they don't want to give up another electron. And so it is, this right here must be a noble gas in order for it to jump here. So it's going to be between the third and the fourth, so you'll count backwards 3 times. Right, so we said third period element, and so we're going to count backwards from neon. 1, 2, 3. Does that make sense? So it has to be aluminum. If we look, let's see if I can fit this in the same page, or same. Is it aluminum? What's the answer to number 30? Yeah, 30 is D. I'm sorry, it's actually on the next page. Aluminum. Right there. So, if we look here, first ionization energy off of aluminum is going to give us magnesium. Second one is going to give us sodium. Third one is going to give us neon. And the fourth one is where it jumps, right? So the fourth one from neon to fluorine is what's going to give us our noble gas. Does that make sense? Good. If we started from something like boron, we'd go 1, 2, and the jump should happen between 2 and 3. Or if we started with magnesium, it should happen between 2 and 1. But it is because it happens with aluminum that it happens between 3 and 4. So this one is an atomic radius question. Arrange these elements in order of increasing atomic radius. So let's look at these guys. We have calcium. We have calcium, rubidium, sulfur, silicon, germanium, and fluorine, right? So we have these random few elements. You can't really even see that. And they want us to arrange them in order of increasing atomic radius, right? And so this requires us to know our periodic trends. Our periodic trends in terms of atomic radius, they like to increase this way and this way. So as you go downward, they increase, and as you go from right to left, they increase, right? So we should see immediately rubidium should be one of our largest ones, right? 31 is what? Yeah, rubidium should be one of our largest ones. So we can definitely cancel out fluorine, because fluorine should actually be one of our smallest ones, right? And then silicon doesn't make much sense either, so we're going to cancel these out. Let's look here. Fluorine, silicon, sulfur, calcium, germanium, rubidium. So what they're disagreeing about between these two answers is calcium, germanium, and sulfur and silicon. So again, as we remember, our atomic radius increases this way and this way. So our calcium should be bigger than our germanium. And our silicon should be bigger than our sulfur, right? And so silicon has to be larger than sulfur, calcium has to be larger than germanium, so A has to be the answer. Make sure you pay extra attention to whether, oh sorry, I highlighted the wrong one, oh my god. Make sure you pay attention to the way that they're asking you, if it's increasing or decreasing, because that definitely makes a difference. Which outer electron configuration would you expect to belong in a reactive metal where N is the shell number, right? So this right here doesn't actually matter. This is the electron configurations that we're looking at. And reactive metals are where in the periodic table? They're going to be on our left, right? So they're not going to really have a P block, because all these guys that have P blocks are like halogens or metalloids or really non-metals, right? So these guys are not going to have a P block. So look here, the only one that really makes sense is D, because anything in the S block is going to be our reactive metals. Anything in the P block is going to be a non-metal. Okay. Chapter 9. So this is kind of, I included these specific Lewis structures because they're things that people like to, or not like to, people get really tripped up on them because they're notable like exceptions to things. So SCO2, well, let's try to draw it as we normally would, right? So selenium has how many electrons? It has 1, 2, 3, 4, right? And then oxygen has 1, 2, 3, 4, 5, 6, but we have 2 oxygens, so we're going to do 2 times 6. This is going to lead us to have 16 electrons in our Lewis structure, right? Obviously, our skeleton looks like this. So most people, yeah.
Does selenium have 6?
Did I mess up?
Yeah.
It does have 6, thank you. 6. That's going to be 18. Thank you, guys. So we're actually going to be using 18 electrons here. And most people would want to make it look like, what they would do is they would try to give everything a complete octet like this, right? So this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, right? But then oxygen doesn't have a complete octet here, right? That's the first problem that we run into. So we're going to start with double bonds like this, right? So what this actually winds up looking like is that oxygen has 1, 2, 3, 4, 1, 2, 3, 4, which gives us 8, 10, 12, 16, 8,
You said
14, 16, and then 18, right? But this actually isn't the Lewis structure for selenium. For some strange reason, selenium doesn't like to take on 6 electrons, even though it technically can, because of the fact that it's a 4th period element, but it doesn't like having that expanded octet like that. So what it's actually going to do is it's going to resonate. Like that. The textbook never really explains why this happens, and I can't really figure out a reason why it happens either, but I remember seeing it on my final. So this is something that I would keep in mind. It's just one of those structures that just seems to not follow the rules.
So would that be the answer, or would that first?
This is the answer. Yes, this is the answer. Yep.
Are you using the octet for selenium now, though, on that?
Yes, I am. Thank you. Like that. The reason why people like this much more is because everything here has a 0 formal charge, right? Like it looks proper. And selenium is able to have an expanded octet, so this looks better. But even though this looks weirder, this is correct. Okay. And then the Lewis structure for CO3 2-. Important thing to keep in mind when they ask you for a Lewis structure is that if it has resonance structures, you have to draw all of the resonance structures in order to get the proper Lewis structure for it. So CO3 2-, our carbon is going to have 4, and our oxygen is going to have what? Our oxygen is going to have 6 times 3, right? Because 3, so it's going to be 18. And then we have a 2- charge, so we're going to add 2 to 4 plus 18 plus 2. So we're going to have 24 electrons to work with. Yeah, we're going to have 24 electrons to work with. So our skeletal structure will probably look like this. So let's try to give everything a nice octet before we do anything first, right? So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So the first problem that we run into is oxygen doesn't have a complete octet here. And nothing has a pretty formal charge. Everything looks wonky. So I'm going to start by moving this lone pair to a double bond here. Right, so now that lone pair no longer exists. Now, carbon has a 0 formal charge, oxygen has a 0 formal charge, and these two oxygens have a negative formal charge. Rule of formal charge is that if you have to give something a negative formal charge, give it to the most electronegative atom. Oxygen is pretty good at stabilizing a negative charge that way. So that's why it's most stable in this arrangement. And because it has a -2 charge, we're going to have to put it in brackets and put that charge up here. Also, this double bond resonates around this structure. So it'll take its time going around. Like that. Good? Yeah. All right. 35, use formal charge to identify the better Lewis structure. So they want you to figure out which one looks better here, right? So formal charge, hydrogen, the way that formal charges usually work is that if you snip this bond in half, right, you're gonna give 1 electron to hydrogen and 1 to carbon. And you do that with every single bond that you see, right? So carbon is going to get half of all of these bonds, right? So that's going to be 1, 2, 3, 4, because you have a double bond here. Carbon wants to have 4, so it has a formal charge of 0. Hydrogens each have a formal charge of 0, because it has 1 electron. They want to have 1 electron. And sulfur likes to have 6. And so 1, 2, 3, 4, 5, 6. This has a completely perfect formal charge, as opposed to this one. Sulfur wants 6, but it only has 1, 2, 3, 4. So this has a +2. These have 0. Carbon here has a 1, 2, 3, 4, 5, 6 when it wants 4, so it has a -2. So while the net charges cancel out, the first structure is a lot better in terms of Lewis structure. 36, they want you to draw the Lewis structure for, I don't even know how to say that, triiodide. So iodide has 7, and we have 3 of them, so it's going to be 21, but it has a negative charge, so when we add 1, we have 22 electrons to work with. The skeletal structure is going to look something like this. All right, so 1, 2, 3, 4 have already been used up. 5, 6, 7, 8, 9, 10. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22 is how this guy is going to look. And this works because this has a formal charge of 0, this has a formal charge of 0, and this has a formal charge of 1, 2, 3, 4, 5, 6, 7, 8. This has a formal charge of, does that work? Yeah, -1. And this is okay. It breaks the octet rule. But iodide is all the way down here, and it does have an expanded octet, so it's okay for it to take electrons on that way. This is going to be the proper charge. And iodines are pretty electronegative. So the fact that this has an abundance of electrons is okay because it's going to stay stabilized throughout the molecule. Good. 37. A Lewis structure for the acetate ion is shown here. Which structure is the best resonance structure for the acetate ion? So if we look at this guy, a lot of things go into finding what the best resonance structure is, but for the most part, something that's super important is formal charge. Formal charge is always super important. So I'm going to start assigning charges like this. This guy has 2 too many electrons, and this guy has 1 too many electrons. So because carbon likes to have 4, oxygen likes to have 6. This one has 6, and this one has 7, right? This guy cannot possibly be right, because if you look here, carbon has 10 electrons, and it does not have an expanded octet, so B is out of the question, right? This guy has a 0, formal charge 0, 0, 0, 0. This one has a -2. This one has a -1. And then this one has 0, 0, 0, 0. This one has a -1, 0, 0. So the answer here should actually be D. Because while none of them are perfect, the only formal charge in D is on the most electronegative atom, right? Here, carbon has a -2 formal charge, making it very unhappy and very reactive. So here, the answer has to be D. 38, which compound is likely to have an incomplete octet? So this is just another memorization question. As you guys know, like the octet rule is not really a rule because it really only applies to like the first 3 rows. But even within those first 3 rows, aluminum and boron are allowed to have 6 electrons at times. They're perfectly stable that way. Whereas carbon, if it only had 6 electrons, it would probably be like explosive or something. But boron and aluminum are the central atoms that are okay with having an incomplete octet. So the only one here that makes sense is B. Chapter 10, which of these has a dipole moment? So dipoles are kind of tricky because people like to look at them using Lewis structures. But while you can do that, you also have to keep Vesper theory in mind. So if you look, let's start from the bottom and go up. If we have sulfur tetrafluoride, carbon dioxide, we have methane, and then we have, I'm going to draw this down here, CH. Right. So if you remember, this has, I believe it's an octahedral geometry. This one has linear. This is an H, by the way. This one has tetrahedral, and this one has tetrahedral, right? So this one is perfectly symmetrical. Everything cancels out because of the fact that it looks kind of like this. Right. All of the moments cancel each other out. This one, they go this way, so that cancels each other out. This one, they all go in different ways, so they all cancel each other out. However, in A, although they make a tetrahedral arrangement, this one and this one for Cl are much stronger than the moments for hydrogen. And so these vectors actually don't cancel each other out, and they have a very strong dipole moment going on. So it has to be A. Do you guys understand why that doesn't cancel out with tetrahedral geometry? Yes? So the point made here was that, okay, so B is tetrahedral, right? But because all of its atoms are the same, it's okay because all the vectors cancel out, right? But A, even though on paper, when it's perfectly flat, it looks like these cancel out, if you envision a tetrahedral in your head, it's kind of like 2 pointing upward and 2 pointing downward like this. The 2 pointing upward don't cancel the 2 pointing downward properly. Another good resource for you guys to look at for Vesper is called Mol View, MOL View, and it's kind of like a molecular model kit but online, so you don't have to buy anything. It's really nice. I use it all the time. Yeah, that's helpful. Okay, we're almost there. Why or why not is the following structure a valid ball and stick model depicting molecular geometry? So A and C say that it is a valid structure, and B and D say it's not, right? So let's look through these. It is because lone pairs are taken first from the equatorial positions, as they should be, right? So this second part is, hold on. Second part is true. Equatorial positions, I don't think I wrote this correctly, are placed. Sorry, that's totally what I meant to say. Placed first on the equatorial positions, as they should. B, it is not because the lone pairs are right next to each other, and lone pairs should be as far apart from each other as possible. C, it is because this is the model that minimizes repulsion the most. D, it is not because lone pairs should be taken from the actual axial position first.
Is front supposed to be on?
On, yes.
Yeah.
And so, actually, I think I may have written this incorrectly, because in that case, both A and B would be correct. So I'm going to start with these two, and I'm just going to explain what a valid ball and stick model would look like. This is not the model that minimizes repulsion the most. If you wanted to minimize repulsion the most, you would put the lone pair here and here, not right next to each other. You see how there's only 90 degrees of separation between these two? If you wanted to minimize repulsion the most, you would make it 180 degrees, right? So C can't be the answer. Lone pairs should not be taken from the axial position first. Oh, I see what I did here actually. So neither A nor D can be correct, is the point that I was trying to make, because in an octahedral model like this, it doesn't really matter where you take from first. It matters when you have a trigonal bipyramidal geometry in which you have a trigonal pyramid. But in an octahedral geometry, it doesn't matter, because no matter how you orient this, any of the axes can be axial, any of the axes can be equatorial. So A and D can't be the answer. And then B, it's true, the lone pairs are right next to each other, and lone pairs should be as far apart from each other as possible. So that's why your lone pair should be 180 degrees from one another. Does that make sense? Kind of. Answer's B, sorry, yeah. Okay. Consider the structure of the amino acid aspartic acid. Indicate the hybridization about each interior atom. So this is like this, right? So when we look at one, what's important to note here is that they will not show you lone pairs, so you have to draw them in, right? Like that. So right off the bat, that's like a small trap that you could fall into. If you didn't draw the lone pairs on oxygen, you would think that it's sp hybridized. And the way that we determine hybridization is the number of domains, or the number of bonds and lone pairs that it has, determines hybridization, right? So this has 1, 2, 3, 4 domains, which makes it sp1, 2, 3, which is sp3. Does that make sense? And so this guy here, if we hadn't drawn the lone pairs, it would be very easy to just say sp and then move on. But this is actually sp3 because of the fact that it has 2 lone pairs. So knowing that, 1 can be eliminated, and A and D can be eliminated, right? So first one has to be sp3. Second one, here, carbon is attached to one oxygen, one carbon. It only has 3 electron domains, so it's going to be sp1, p2. So sp3 hybridized, sp2 hybridized, I'm sorry, sp1, 2, sp2 hybridized. This is sp3, so it can't be B. Apply molecular orbital theory to determine which molecule is diamagnetic. So the way that MO theory works is that, I wonder why I didn't write that down. You don't? How about you guys? You do have to know it? Does it depend on the professor that you have, do you think? It sounds like Hyder doesn't want you to know it. What about like Patino or Saida?
Did you ask again?
Molecular orbital theory? Does he expect you to know that?
He did it.
He did it? It's that thing that looks like this.
Yeah, we definitely did that in class.
You did it in class? Okay, then I want to go over it with you guys. Okay? Good? Okay. So diamagnetic and paramagnetic are 2 different things. People get this confused pretty often because for some reason it's hard to remember that para means only one and dia means paired. Right, because para sounds like paired electrons. So a diamagnetic would look like this and a paramagnetic would look like this, right? A diamagnetic molecule means that there are no single electrons anywhere. They're all paired up. Whereas a paramagnetic molecule, even if there are paired electrons, if there is one unpaired electron, it is considered paramagnetic. Does that make sense? So the way that molecular orbital theory works is that you put your atoms on the side like this. So you put your atoms on the side like this, right? So carbon has 4 and oxygen has 6, so you need 10. You're going to have sigma, anti-sigma, right? Then pi, pi, anti-pi, anti-pi. And you start from your lowest. Actually, I think I have these flipped, sorry. This is pi, this is pi. You're going to have 1 sigma like this. And so, oh my God, what am I doing? I'm going to rewrite this. Yes. Right. Carbon has 4 and oxygen has 6. So we're going to start from here. We're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So carbon dioxide is diamagnetic, as we can see, right? Because none of these are unpaired, right? Whereas something like boron, which has 3, right? So I'm going to do this again. Boron, which has 3. Oh my God, I'm sorry I keep miswriting this. Anti-pi, anti-pi, and then anti-sigma, which has 6. 1, 2, 3, 4, 5, 6. Wait, that doesn't make sense either. We're going to come back to this one. I want to make sure we finish the gas laws unit, but we're going to come back to this one. The answer to 42 is A. So 43, which gas sample has the greatest volume at STP? There is this rule in gas laws that says that 1 mole of any gas occupies 22.4 liters. It doesn't matter what kind of gas it is. 1 mole of any gas is going to occupy 22.4 liters, right? So this is confusing because this isn't in moles, it's in grams. So although they look similar in the way that they're presented, when we convert them to moles, they are going to have different numbers or different volumes that they take up, right? I forgot to give you your molar masses for this one. So argon, krypton, and xenon. Essentially, what my point is here is that for every 1 mole of argon, you have 39.948. For every 1 mole of krypton, you have 83, right? For every 1 mole of xenon, you have 131. So as you get heavier and heavier, you're going to have less and less moles of gas for every 10 grams. Does that make sense? And so you're going to pick the one with the smallest molar mass, which is going to be argon. 43 is A. 43 is A. Because 10 divided by a smaller number is going to give you a larger number for your number of moles. Does that make sense? I'm going to do the math out, actually. I don't want to confuse you guys. 1 gram of argon is going to give you 10 grams of krypton is going to give you and then 10 of xenon is going to give you. You see how as your gas gets heavier, you have less and less moles per 10 grams, right? And so if at every 1 liter, every 1 mole you have 22.4 liters, then with a smaller number of moles, you're taking up less amounts of space, right? So the one with the greatest volume is going to be the one with the largest number of moles, which is going to be argon. What is the pressure of 1.78 grams of nitrogen gas confined to a volume of this at that temperature? What we're going to do is I give you your molar mass, so you're going to turn grams into moles. Nitrogen gas is N2. It is not just N. That is another trap that usually gets people. So make sure you're using the correct molar mass. They should be giving it to you, but in case they don't. 1.78 divided by 28.02 is going to give me that many moles of nitrogen gas. So this is my N, right? Knowing my gas law, PV equals nRT. We have to find P. So P is equal to nRT over B, right? We just found our N. So it's going to be 0.0635 moles. Our R is 0.8206 liters ATM, moles Kelvin. And then our T, this is in Celsius, and we have to make sure that we convert that to Kelvin, 298 Kelvin. And you guys know that in order to convert Celsius to Kelvin, you just add 273, right? And then our volume was given to us in liters. Make sure everything is in SI units, and you should be good. When you multiply this across, 0.0635 times 0.08206 times 298 divided by 0.118. You should get 13.2 ATM. So our answer C. A 1.25 gram gas sample occupies 663 mils at that temperature and pressure. What is the molar mass of the gas? So what we need to do is find, using this information first, right? Using this information first. We're going to find our N, which is our number of moles that we have. Once we have found our number of moles, we can divide our grams by the number of moles in order to get our molar mass, right? So if they ask us for molar mass, which I'm going to denote by mu, mu is going to be grams per mole. We have grams, which they give us here, but we don't have moles, which is what we're going to find using our gas laws, right? So this V is actually 0.663 liters, T is 298 Kelvin, and P is 1 ATM. So I've done the converting here. So if PV equals nRT, and we need to find N, then N equals PV over RT, right? So I'm going to plug in 1 ATM, 0.663 liters, 0.08206, and then our temperature is going to be 298. Which is going to give me my N, right? Once I've found my N, I'm going to take my grams, 125 grams, and I'm going to divide it by my number of moles here. 125 divided by the answer I just got. It's going to give me 46.1. Which is D. So these two are connected. 46. So kinetic energy is actually just a measure of how much temperature, or temperature is actually just a measure of how much kinetic energy something has. So although we like to think of temperature as something that's related to heat, it isn't always. Something that just has a lot of kinetic energy has a really high temperature. That's like the textbook definition of it, right? So which gas has the greatest kinetic energy at, where's my answer key? At STP. And it's just that none of them has the greatest kinetic energy, because kinetic energy is proportional to temperature. And STP, standard temperature pressure, is a pressure of 1 ATM and a temperature of 0 degrees Celsius, which is 273 Kelvin. All of these are bouncing around at the same temperature, right? So that's why our kinetic energy is the same for any gas at STP. But which gas has the greatest velocity at STP? We like to think of these as the same thing, but kinetic energy is actually 1/2 mv squared, right? So velocity and kinetic energy, while all of these have the same kinetic energy, these guys all weigh different amounts, right? Like helium is lighter than neon, which is lighter than argon. So knowing that if we have to keep kinetic energy equal and our mass increases as we go from helium to neon and neon to argon, then our velocity needs to decrease in order to compensate for that, because these have a directly proportional or an inversely proportional relationship, right? So the one that has the greatest velocity is actually going to be helium, because while it has the smallest mass, it's going to have the largest velocity in order to make up for that, in order to keep our kinetic energy the same. Does that make sense? Okay, thought I was going to run out of time, but I didn't. Do we have any, so we have about 12 minutes left. Do you guys have any problems that you would like me to go back to and look over? Oh yeah, 42. Okay. Where's my phone? I am actually going to look this up to make sure I'm not telling you guys something incorrect, because I forgot to write it down. Apply molecular orbital. Aside from 42, is there anything you guys want to look at?
Could we do one from chapter 7 where you find the energy like in joules and like number of volts and like a different problem concerning wavelength.
A different problem concerning wavelength. So I didn't actually bring any other problems with me to do. I mean, What might be helpful for you is that there is another Chem 1 tutor. Her name is Laura. And if you look on the UCF Study Union website, and you go under her name, she should have her own test up. And so
Which website?
it's, okay, so it looks like it's UCF Study Union.wordpress.com. And again, the other chem tutor's name is Laura. I don't remember what her last name is. But she should have another test up. And that would help you with, yeah, yes.
I couldn't find this real online.
You couldn't find it online?
No. It's that makes like a file of Google Docs that's up on the web website.
Really?
Yeah.
Um,
Like it's showing me like a document that's really chapter 5.
mm-hmm. That's weird. Let's see. Mm-hmm. Why isn't this working? Oh, here it is. So if you control F, so this is the link, Study Union. So this is, if you control F my name,
Oh, okay.
right, this should come up like this.
Oh, okay.
Yeah. Did you go to the SARC website instead?
Yeah.
Okay. Okay, that's why. Yeah. I think it's something different up there, and yeah, it was on my drive, so I got rid of it.
Okay.
Yeah.
Thank you.
Mm-hmm. So for 42, I was actually drawing the orbitals incorrectly. I'm sorry. For 42, the way you're supposed to draw these is that you have S and you have P, right? And so your S's line up to make sigmas. This is sigma anti, and this is sigma. And then your P's line up to make sigma pi, sigma antis, like this. Right, so if we look at something like CO, so if we put C on this side and we put O on this side, carbon has 2 electrons in its s orbitals, and it has 2 electrons in its p orbitals like this. Whereas oxygen has something that looks like 1, 2, 3, 4, right? So what I basically did was I drew its electron configuration. It has 2 in its s and 4 in its p, whereas carbon has 2 in its s and 2 in its p. And so knowing that I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons to work with, I'm going to start filling it in like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Which is why none of these are paramagnetic. These are all diamagnetic. If I look at something like B2, boron has 1, 2, 3 in all of its electron configuration, right? This is its anti, this is its anti. Right? So I only have 6 electrons to work with, which makes it go 1, 2, 3, 4, 5, 6. If you look here, these guys are unpaired, right? So what I did was I literally looked up molecular orbital theory, and it can show you how you're supposed to orient your molecular orbitals, right? So what I was doing is I was forgetting that these guys have S sigma bonding orbitals. And I was going straight to the P. But if you just search up molecular orbital theory, you're able to see how you should be drawing your molecular orbitals. And from there, you just fill in using Hund's rule, which tells you any degenerate orbitals need to be filled singly before they get paired, right? So that's the molecular orbital theory problem. There's never more than 1 or 2 questions on that for final, so don't sweat it too much.
What about gas diffusion and diffusion? Does that ever show up?
Kinetics, I'm pretty sure it's a Chem 2 topic.
Okay.
Yeah, that's like right on the cusp of Chem 2. Pretty sure that's Chem 2 topic. Okay, thank you. Yes. Yes, thank you for coming today, guys. Yes. I don't think so, yeah. Just a quick reminder, guys, make sure you take our survey before you leave if you can. But thank you so much for coming. And best of luck on your final. Maybe you were saying, for what?
So I was just on that website for Study Union, and for all the other tutors for Chem 1, you uploaded your answers, but I don't think the other ones did.
So they do that because they want you. They want you to come to their session,
Gotcha.
right? So if you come, you're supposed to get the answers. I just figured, even if I have the answers up, if you don't know how to do it, you're not going to be able to do it.
Yeah.
So I uploaded it. I don't think so, unless you decided to email SARC themselves and let them know. I don't know if they would be willing to disclose it either, but I'm not really sure. I'm sorry. I don't think so. Would it be helpful, do you think?
Yeah, but if you're not going to do it, I was wondering if I could just take a picture.
Yeah, actually that would be easier just because I don't really have a scanner, and yeah, but you're going to want to take a look at that. Yeah, thank you guys so much for coming today. Was it okay?
Yes.
I know I was speeding through it.
No, you got through all of it.